Hi everyone, let's go through your first midterm. On the whole, pretty good, okay. My kind of rule of thumb is that anything over 100 is pretty good. Chemistry 102, obviously, we are graded on a curve, so don't worry too much about your absolute score, just where you are in the big scheme of things, okay. So anything over 100 is good. Check Canvas for, where you rank in class and where those lines are drawn for grades, all right. So we're going to go through it. Now, most of you are doing fine with the work, but do make sure you show all work as advertised, okay? Significant figures and all that, right? So chemistry is all about details, right? So obviously 2 tests, A and B. I'll go through both, all right? Sometimes the answers are the same, all right? But where they're not the same, I'll look at the other one, all right? So for the first, and I did tell you this when we looked at it in the video, right? I said, hey, expect something essentially identical on the exam, and here it is, right? So if you just looked at that example in the video, you'd have got this, right? So express rates, right? So the rate is, we just put in the stoichiometry, 2 to 1 essentially, so, bring it all down to the same level, minus a half because it's a reactant, plus a half, plus a half because it's 2, and then 1. Okay, so the rate is these things, all right? And I remember we actually look at maybe one of these individually when we get a number from an experiment, and then we can just do some algebra. And that's what we did down here. So when N2's increasing at this, what is this decreasing? Well, you have that little bit of the relationship, and then just move things around, given that this is what we were given, and you get the answer, okay? 1.63 moles per liter per second. On the other one, ask you a different thing, but it's 3.88 moles per liter per second. All right. Now, the Arrhenius, very, very similar to what we did as an example, right? Okay, so I don't stray too much off what we do in the packets, right? So, like, activation energy is this, how many times faster, that's that how many times faster example, right? So, activation energy is 25.8 kilojoules per mole, so I like to write 25.8 times 10 to the 3 joules per mole because we use metric R, right? There it is. Put it in Kelvin for the temperatures. Remember, because it's K2 over K1 and coupled with that T2 and T1, there's the equation from the back, right? You gotta make sure T2 and K2 are the bigger numbers, right? So bigger number, yeah, okay. All right, so basically just stick the numbers in and rearrange, right? We did that one in the class, followed it through. The ratio K2 to K1, which is proportional to the difference in speed, is 1.57, so then you just tap that on the end there, 1.57 times faster. All right, now, a couple of people, actually one person, use a different equation here, right? You can't go off and use different equations from the data sheet because that tells me you're looking elsewhere in a textbook or in another note packet or something, right? You can't look at other things when you're taking my test. The idea is there's you, a calculator, and this note packet in front of you, right? Or this exam in front of you. You can't be looking at other stuff. It does specifically say that in the instructions. So if you use an equation from somewhere else that's not on the data sheet, where it's log base 10, for example, you don't have that stored in your head. You looked it up. Come on. All right. So there are significant deductions if I know you went elsewhere for data. Okay. Don't do that. Don't Google stuff. Don't look at other material while taking the test. All right. Now on the other one, very similar, but it was 2.73 times faster. Okay. All right. Initial rates, on the whole, initial rates was really well done. I kind of did a combined method here. So we're asked a bunch of things. There's our data table. Find the rate of each, find the order with respect to each one. Okay. Summarize that in terms of a kind of rate law expression or rate equation. Find K with units, and then find the rate under specific conditions. All right. So, I did the dividing 2 to 1 there. In the traditional way, to find M with respect to A is 1. And I just did it for observation, right? So this is 4 times this, 4, 2 to the N is 2, no change, 0, and I got this one, right? On the other one, I switched the columns essentially. So you got 2, 1, 0, right? Okay. Then, remember that's anything to 0 is 1, so that's okay for math now, right? So K is rate over this. You can pick any line you like. I just picked the first line, stick the numbers in. Remember, it's essentially cubed underneath, and the units are m to the minus 2 seconds to the minus 1. You've got to get the right units, otherwise you didn't get the 4 points there, okay? Then hey, when everything's 0.75, now you have k, stick it in here essentially, but you got k, right? There it is, with the units. Out it comes, 3.9 times 10 to the minus 3. On the other one, a squared, b to the 1, that was different. We arranged to find k, 9.4 times 10 to the minus 3 moles per liter, minus 2 seconds to minus 1, and then 3.2 times 10 to the minus 5 for the rate. Okay. Number 4, integrated rate law. Okay. So, you know, if you recognize it's an integrated rate law problem, just use the equations from the data sheet for the first order. I did say first order. Okay. K in terms of half-life, rearrange, stick in the numbers, units of seconds to the minus 1. Because if the units of half-life are in seconds, second to the minus 1 must be K, right? Okay. On the other one, different numbers, 2.19 times 10 to the minus 2 seconds to minus 1. Then you just use the first order integrated rate law equation, okay, which is given. You got to basically find AT, list my variables. Remember, it's in seconds up here for K, right? We find second to the minus 1. So we had to turn 3 minutes into seconds, which everyone did. 180 and then 120 on the other one. So here's our destination. Just follow it through, do the math. 1.1 times 10 to the minus 1 moles per liter. Other one here, 120 seconds, follow it through, 2.68 times 10 to the minus 2 moles per liter. Okay. Again, freeze, you know, if you want to check the math out. Last one, on the whole, the solution to the question was pretty good. Remember my little trick here, I always like to kind of list my variables in the margin, you know, kind of sort of optional, but it's a nice thing to do. Okay, so I have to find, you know, so calculate the osmotic pressure for 87.5 milligrams of hemoglobin and 10 milliliters at 25. Molar mass is this, right? So osmotic pressure, obviously we're going to set it up and solve for pi here, right? But before we do, we need the concentration, molarity, right? So I need first, grams divided by molecular weight is moles. Fair enough, right? Okay. And then, hey, concentration is moles per liter. So divide by the number of liters is 10 milliliters, 0.01 liters, right? And there. Okay, so that's my concentration. Then I'll just stick them in. If you leave the units in, which is great, right? They all cancel to give you atmospheres. Some people try to convert to torr. That's okay, but you didn't have to because atmospheres will just pop out here. All right. On the other one, very similar, but obviously, you know, different mass. So different number of moles, 6.7 times 10 to the minus 7, 6.7 10 to the minus 5, and then 1.6 times 10 to the minus 3 atmospheres. Okay. So again, you know, feel free to pause, right? Feel free to pause when you're going through this to check your answers against mine, okay? And if you think I misgraded it, yeah, you can get a regrade. But remember, okay, make sure you're absolutely sure because it's, you know, if you get the same score or less when I regraded, it's a minus 10% penalty because I don't want 72 regrades every time I do a test, okay? If you've got questions, feel free to come to the office hour. Anything, right? So anything to do with your midterm, happy to talk about it at your office hour. Okay, stop there. See you guys next time.